In this video we are going to see working of the Daniell cell, that is the cell reaction. When the two electrodes are connected to the external circuit by a metallic wire, the following oxidation and reduction reactions takes place. Let me see the first oxidation reaction, that is oxidation at zinc electrode in the half reaction. In this reaction, the zinc has a greater tendency to ionize than that of the copper, and so the zinc atoms from the metal rod rush in ZnSO4 solution as oppositely charged zinc ions and leaving behind electrons at the zinc metal rod. This is the process of oxidation, that is it gives the Zn gives Zn2 plus 2 electrons, and the electron remains on the zinc rod and the rod becomes negative terminal of the cell. This cell reaction, which is also called as anode of the cell. Second one is the reduction at copper electrode of the half reaction. In this reaction, the liberated electrons at the zinc electrode travel towards the copper through the external circuit. In that, the Cu2 plus ions in the solution of copper sulfate go and get a deposit on the copper rod and get discharged by taking electrons coming from the zinc rod. This is the process of reduction, and it will be given, that is Cu2 plus 2 electrons gives the Cu. This is the reduction process. In that, the metallic copper formed in the reduction process gets deposited on the copper rod and the copper electrodes become short of electrons and becomes positive terminal of the cell. It is also called as the cathode of the cell. For this oxidation and reduction process, it will be given as the net cell reaction. In this net cell reaction, the oxidation of zinc takes place at the zinc electrode and reduction of copper takes place at the copper electrode, and the overall net reaction which be written by adding the two half cell reactions, that is Zn plus Cu2 plus gives Zn2 plus Cu, means at the anode it will be given Zn solid, it gives the Zn2 plus 2 electron in oxidation reaction half reaction, and the second at cathode Cu2 plus 2 electron, it gives the Cu solid at reduction half reaction. If we adding these two reactions, that is net cell reaction, it gives the Zn solid plus Cu2 plus, it gives the Zn2 plus Cu. This is the overall net cell reaction, and it is the convention that the current in the external circuit is considered to flow from the positive to the negative electrode, that is copper to zinc electrode. Current is flow from positive to negative electrodes, although the electrons are flowing through the wire of the opposite direction. Next, we can see the convention used to represent a cell. A voltaic cell, which is made up of two half cells or two electrodes. It is not always convenient to represent the cell diagrammatically, so the following are the conventions are used to represent a cell. We see the first convention: when the negative electrode or electrode with oxidation potential, which is written to the left hand side, that is left, this is called as the left hand electrode in the cell, and these electrodes, which is oxidation reaction, takes place. Second convention: the positive electrode or a electrode with lower oxidation potential is written to the right, which is also called as right hand electrode in the cell. At this electrode, reduction reaction takes place. Third convention, the single vertical line between the electrode and salt solution or in between the two salt solution, which is indicate the direct contact between them. For example, Zn single vertical line ZnSO4 aqueous, single vertical line CuSO4 aqueous, Cu plus, means this single vertical line shows that the direct contact in between these two solutions. Fourth convention is that the double vertical line, which is represented between the two salt solutions, which is indicate the indirect contact between them. This is the way by which the salt bridge in setup or the cell can be represented. For example, ZnSO4 double vertical line CuSO4 Cu plus. This double vertical line is represented as also the salt bridge, and which indicates that the indirect contact between these two salt solutions, that is CuSO4 and ZnSO4 solutions. Fifth convention is that in case of gas electrode, the inert metal conductor is always incorporated in the convention. So the example is that the hydrogen electrode, which is consist of dilute HCl solution in which platinized platinum foil is dipped and over which hydrogen gas is bubbled. This electrode can be written as platinum H2 single vertical line HCl or also platinum H2 H plus aqueous. Similarly, in case of chloride electrode, platinum Cl2 Cl minus aqueous. The next convention is that when the concentration or activities of solution and pressure of gases are required, these are written in the brackets, that is the concentration of ZnSO4, which is written in the bracket 0.1 molar. The pressure of the gas, which is written in the bracket, that is 1 atmosphere, and activity, that is activity of H plus ions is 1, which will be written in the bracket. Concentrations or activities of the solution and pressure of the gases are required, and these will be written in the bracket. And these are the examples of these, that is ZnSO4 concentration written in the bracket 0.1 molar, salt bridge CuSO4 0.1 molar Cu plus, and pressure of the H2 is 1 atmosphere, activity of H plus is 1. These are the examples. Next convention is that for a cell with spontaneous reactions, flow of electrons is from left hand electrode to right hand electrode, that is anode to cathode, that is oxidation electrode to the reduction electrode. And in this case, EMF of such a cell is always positive. So under this condition, it is by convention that current in the external circuit is considered to flow from right hand electrode to left hand electrode, and this is the example of this. In this example, we can see that the reaction is that ZnSO4 salt bridge CuSO4 Cu plus. In that, the electrons is moved from zinc to copper, that is negative electrode to positive electrode, and current will be flow from positive electrode to negative electrode, that is reduction to oxidation. Next convention is that EMF of the cell. In that case, it is the sum of oxidation of potential of left hand electrode and the reduction potential of right hand electrode. Oxidation potential of left hand electrode and reduction potential of right hand electrodes, and this will be represented as E cell is equals to E oxidation of left hand electrode plus E reduction of right hand electrodes. Also, the EMF of this cell in case of potential of both electrodes are stated in oxidation or reduction potential. Both potential will be different. In that case, we can write, it means the EMF of the cell, it will be written as E cell of the left hand electrode plus right hand electrode of the oxidation potential. And if in the case of the potential of both electrodes are stated in case of both electrodes are shown in oxidation or also the both electrodes are shown in reduction potential, in that case it will be written as, if the oxidation potential is given, both are stated as a oxidation, so the cell reaction will be written as E oxidation left hand electrode minus E oxidation right hand electrode. Or in case of the EMF of the cell, in that case, if the both potential will be given as the reduction potential, in that case the EMF of the cell will be written as E reduction of right hand electrode minus E reduction of left hand electrode, and this is the rule which is called as the plus left minus right rule. These are the some conventions of the cell reaction which is represented. Next, we can see reversible and irreversible cells. In that, we already seen that the electrochemical cells. The electrochemical cell shows the two types of the cells. One is the reversible cells, another one is the irreversible cells. This classification, which is based on the concept of thermodynamically reversible processes, means the process which is said to be thermodynamically reversible and provided that the driving and opposing forces are only infinitesimally different from each other, and that is, it is possible to reverse any change taking place by applying an infinitesimally greater force than one of the actually acting. So, the cell which is said to be reversible when it is satisfied the above conditions, means we see the reversible cell which is called as the electrode reactions and cell reactions are reversed, in that the chemical reactions which is occurring in the cell may be proceed in either direction depending upon the direction of flow of the current. When the circuit of the cell is closed, the reaction occurs in the cell and the current or electricity is produced. Therefore, if the driving force is applied from an external DC source where EMF is greater than that of the cell, then the current will flow from opposite direction and the chemical action is fully reversed. This process, wherein driving force is infinitesimally greater than that of the opposing force and which is carried out at very slowly. When this requirements is satisfied, then the cell is reversible, and its example to illustrated that the Daniell cell, that is Zn plus Cu2 plus is equals to Zn2 plus Cu. This is the reversible cell. Next, we see the irreversible cell. In the irreversible cell, it is represented as, it is the original state of the cell and it cannot be produced. So the reaction, it is not reversed. In this case, the chemical process cannot be exactly reversed by the application of external EMF which will be considered. And if we composed the zinc and copper electrodes which are immersed in the solution of sulfuric acid. When the two electrodes are in short circuited, the zinc dissolves with evolution of hydrogen at copper electrodes and it gives the Zn solid plus H2SO4 is equals to ZnSO4 plus H2 gas. Also, in the case of the cell is connected with the external source of potential slightly greater than its own, then it means the copper dissolves at one electrode and in that case the hydrogen is evolved at the zinc electrode and the cell reactions becomes Cu plus H2SO4. It gives the CuSO4 plus H2 and this is the irreversible cell. These two equations shows readily evident that the original state, that is of the cell, cannot be produced and the reaction is not reversed and this is the irreversible cell. Next we will see the term measurement of EMF. So what is the electromotive force, that is EMF? It is defined as the difference of potential which causes a current to flow from the electrode of higher potential to one of the lower is called as electromotive force of the cell and which is expressed in a Volts. So the measurement of EMF which is used by the potentiometric method, and these potentiometers for EMF measurements which is operates on Poisson-Drought compensation methods. By using this principle, the unknown EMF which is opposed by another known EMF until the two are equal. So this is the setup for Poisson-Drought compensation method for measuring the EMF. In this method we can see the storage battery B of known EMF. EB is connected to a resistance wire AB of uniform cross section. The storage battery B must be supply constant EMF and it must be greater than that of the cell under consideration. When the experimental cell X is also connected to A having positive pole in the same direction as a storage battery B and sends currents in the same direction. The two EMF thus oppose one another. So to find the unknown EMF, that is EX of the cell X, the sliding contact between the C is moved along AB until the position S is found at which the galvanometer gives no deflection. From EB and the distance AB and AS, the unknown EMF EX is found. To find this unknown EMF EX for any given current B passing through the resistance AB, and EB must be proportional to the length AB and EX may be proportional to the length AS. Therefore EX must be proportional to the length AS. It means by dividing this EX and EB we get the length AS upon length AB and we get the EMF of the EX is equals to length AS upon length AB into EB. This is the unknown EMF EX can be obtained. So to the direct reading of EMF and a direct reading of potentiometer may be used which operate on the principle by using the Poisson-Drought compensation method. Also we see the another case, that is direct reading of the EMF, and this direct reading of the EMF we use the another principle of direct reading potentiometer. So let me see this diagram. In this diagram we can see the principle of direct reading of potentiometer. So we see the AB is a high resistance platinum iridium wire of uniform cross sections, and in this case the battery B, which is also called as the working cell, and this battery B, which is usually an accumulator of constant EMF and which is connected across the wire AB. So the constant EMF of B is thus impressed across the AB through a variable resistance R. The positive pole of the cell X is connected through a two-way key, that is K, and a tapping key K prime. K and K prime. This is the tapping key and this is the key. The positive pole of the cell X is connected through a two-way key, that is K, and the tapping key K prime, and a sensitive galvanometer is G to a sliding contact with C that can be moved along AB, and the negative pole is connected to A. Negative pole is connected to A and positive pole is connected to keys. So in the similar way, the standard cell S may be connected in the circuit by using the two-way key, that is this key. Two-way key is represented as a dot. Two-way key, and the standard cell in use is generally saturated Western standard cell, whose EMF, which is represented as 1.0183 volts. It is necessary to standardize the potentiometric wire AB. This wire is necessary to standardize. For this purpose, how to standardize this wire? First, the potentiometer C is set at a point S dash along AB, corresponding to the value of the EMF of the standard cell, which is 1.0183 volts. Then next, the switch K is thrown to the S side. The switch K is thrown to the S side. The tapping key, that is K prime, is closed gently and F is moved. This F is moved along resistance until the galvanometer shows no deflection. It means at this adjustment the potential drop between the S prime is exactly 1.0183 volts, and the potentiometer has been standardized to read voltage directly. Now this resistance R is left to undisturbed throughout the further measurement. Then the two-way key, that is this key K, is shifted to the unknown EMF of the X side. The key K prime is closed gently, and the sliding potentiometer C, this sliding potentiometer C is moved along AB until points S, at which the galvanometer G shows no deflection. The reading of the calibrated side wire at a S gives magnitude of unknown EMF of X directly. This is the direct reading of potentiometer of the measurement of EMF. Thank you.